I'm going to go ahead and walk algebraically solving one of these, and then the rest of them I'm just going to use my calculator for. It'll just save some time. So for this one, I can either eliminate the x's, the y's, or the z's. So taking a look at the number value, it looks like it's going to be the easiest to eliminate z. So that's what I'm going to go with. So I think what I'm going to do first is use row 1 and 2, which requires that I only multiply this first row by 2. So twice row 1 plus row 2. So I get for row 1, 4x plus 6y minus 2z equals 8. Row 2 stays the same. And this is awesome. This is best case scenario. What happens here is I'm left with y equals 2. So I already have one of the variables solved for. Okay, now at this point you have tons of things that you could do. You could plug in 2 and get a system of 2 variables. I'm just going to go ahead and eliminate z one more time. This time I'm going to use row 2, which I'm not changing, plus twice row 3. And row 2 stays the same. And row 3 I'm doubling, so I get 6x plus 8y minus 2z equals 0. Add these guys together, and we're left with 2x plus 3y equals negative 6. But I know y is 2 already, so I just take this 2, plug it in. 2x plus 6 equals negative 6. So 2x is negative 12, and then I get x is negative 6. Now that I have 2 of them, I can take them, can plug in. I'm going to plug in a row 1. So for row 1, I have twice x plus 3 times y minus z equals 4. So negative 12 plus 6 minus z is 4. I can move z to this side, subtract 4 over here. So then we get negative 16 plus 6, so I have negative 10 for z. All right, so let's just make sure that works. If I plug this in here, I get 24 minus 10 minus 20. 24 minus 30 is negative 6, so that works. And here I have negative 18 plus 8 plus 10, 18 minus 18 is 0. So we're good on both of those rows. So the final answer is going to be negative 6 to negative 10. Okay. Now for the rest of them, I'm going to use row reduced echelon form. So we can go to matrix, edit. We're going to have 3 by 4. So I have 2, negative 2, 6, negative 3, 2, negative 3, 7, 1, 2, negative 4, 8, 6, and I already have it in my calculator. So for this one, notice this last row is 0 equals 1. Once you have that, you can say no solution. I'm going to do one thing. I just want to check and make sure I have my numbers right. 2, negative 2, 6, negative 3, 1, 6. Positive 7, positive 8, negative 3, negative 4, 2, 2, yep. So for B, this is no solution. Okay, because that last row, the last row, 0 equals 1, that's never going to be possible. All right, for this one, C, we have 1, 6, 3, negative 14, 2, 1, negative 2, negative 8, negative 3, 2, 1, negative 8. And let me just check that all my rows are right. 1, 6, 3, negative 14, negative 8, negative 8, 1, negative 2, 2, 1, negative 3, 2. Okay. So for this one, this is awesome because I have all zeros except for the diagonal. This means I automatically have my x, my y, my z because I have 1x equals 1, 1y equals negative 4, z equals 3. So my final answer for this one is 1, negative 4, 3. All right. Now I do have an x, y, z here, so I need to make sure that I have a place saver for all of them. That's going to make my augmented matrix have more zeros. So I have 1, 2, 0, z, and then 0 constant. 1, 3, negative 1, and negative 2 for my constant, and then 1, 0y, 2z, and then 4, and then we do our row reduced. And for this one, my last row is 0 equals 0. You have to be careful. That's different than the one we had before where z equals 1, because in this case, we have infinitely many solutions. So the way we're going to write this one out is we have to look at the equations we have. So from the first one, I have x plus 0y plus 2z equals 4. And from this one, I have y minus z equals negative 2, and then we have 0 equals 0. So both of these have z in them, but I don't have I don't know what z is equal to, so I'm going to let z be my all real number. So the solution is all the ordered pairs or ordered triples x, y, z, such that I'm going to solve for x. So I'm going to subtract 2z from both sides, so negative 2z plus 4. Now I got to solve for y, so I'm going to add z to both sides, z minus 2, and then z is just all real numbers. So there's your set notation for infinitely many ordered triples. And then for the last one here, e, we're going to get 1, 3 by 4 still. All right, so 1, 2, negative 1, 3, 3, 6, negative 3, 9, negative 2, negative 4, 2, negative 6, and let's just make sure I type those in. 1, 2, negative 1, 3, 9, negative 6, negative 3, 2, negative 4, 6. All right, looks good. And for this one, we have x plus 2y minus z equals 3. And then we have 0 equals 0. Okay, so for this one, I think we're going to have to solve for 1. So if I have x equals, subtract 2y minus z. All right, so we solve for one of them. And then for the last part then, for the ordered triple, we still need to do the set notation. So we have all the ordered triples, x, y, z. Such that x equals negative 2y minus z. And then y is all real numbers, and z is all real numbers.